So good morning, everyone. I'm Madhumita of Sarkar from University College London. And today I'm going to tell you about harnessing continuous time quantum dynamics for quantum state control in different platforms. So I'll focus on two platforms. One is the germanium whole spin qubits, and the other is the programmable Rydberg atom arrays. So my first talk is on quantum communication through a germanium whole spin qubit quantum channel. This is a work done in collaboration with my supervisor at UCL, Sugata Bose, and Rupayan, whom you heard today morning. So what we wanted to achieve was quantum communication between two qubits. Now, if you place these two qubits close to each other, obviously there will be crosstalk, and this will lead to various fabrication challenges because the measuring probes comes from the macroscopic worlds, and so if you do a measurement on one of the qubits, it will disturb the other. So what we propose to do is to add a chain of qubits in between the two qubits, which acts as coupler qubits, or the quantum bus, which just acts as a mediator. So traditionally, people has been using electron spin qubits, but in our case, what we do is that we use whole spin qubits, and the difference between electron and whole spin qubits is that electrons reside in the conduction band, whereas holes live in the valence band, due to which electrons have a s orbital character and hole have p orbital nature. And this p orbital nature leads to several advantages in case of holes. The first is like it has the low hyperfine interaction because it gets shielded from the nuclear spin, and also the p orbital nature leads to strong spin orbit interaction, which is good for quantum control. Controlling the qubits, because like they can be easily coupled to the electric field. But the same spin orbit interaction, which tends to be an advantage, is also kind of a disadvantage for quantum communication. So as pointed out in this recent experimental paper, that there has been a lack of studies in understanding how the exchange coupling in the presence of the strong spin orbit interaction behave. And this is what we wanted to study. So as a first step, what we wanted to do is to find an effective Hamiltonian between the two end qubits, which kind of differs from an electron and hole. For the electron, the spin orbit interaction, which leads to the Rashba interaction, comes from a third order effect, and hence it is small. But for holes, it is like a first order effect, which is quite strong, and this leads to a DM kind of interaction. So I'll come to the mathematics of it later, but first let me tell what it does physically is that it leads to some unwanted spin rotation. So the information which you get at the other end, at the second qubit, is kind of rotated. And and also it leads to certain disorders, because you have, if I remind you, I'm using a quantum bus. So I have several qubits. And for different qubits, the spin orbit interaction is not exactly the same. So the quantum channel in this case becomes a bit unreliable. So now coming to the mathematics of it, what it does at the Hamiltonian level is that for electrons, you can model the system, the exchange interaction between these two qubits by a Heisenberg kind of Hamiltonian, where the sigmas are the Pauli matrices and the exchange coupling, as you can see here, is basically isotropic, having just the diagonal elements. But for the whole case, as I told you, it introduces the DM interaction due to the spin orbit coupling. And what it does is that it makes the exchange coupling highly anisotropic, leading to diagonal as well as off-diagonal terms. And I will show you in a little while how these off-diagonal terms contribute to decay in the state transfer. So previously, actually, Sugata was one of the pioneers of this spin chain quantum communication, and he had considered the Heisenberg model, in which he showed that if you look at fidelity, after a certain amount of time, then the maximum fidelity you can obtain is actually quite good, even for spin chains up to 80. But here, as you can see, if you have a random anisotropy, then the fidelity actually drops badly. So what I mean by fidelity is that suppose you begin with one arbitrary state, and then you let it time evolve with the Hamiltonian. For our case, we have the Heisenberg plus the DM interaction. And then you know what is the ideal final state you would get if there was perfect state transfer. So you measure the overlap between the time evolved state and the final state, and this gives you the fidelity of fidelity values close to 1 tends to tell you that you have perfect state transfer, whereas lower fidelity indicates bad state transfer. So, okay, now what we see is that this anisotropy is actually bad for quantum state transfer. So what can we do? And in order to understand what we do, first we try to find an effective Hamiltonian between the end qubits by tracing out the quantum channel degrees of freedom. Now, if you do low subspace perturbative calculation, you will see that you end up with these two states where the quantum burst tends to remain in the singlet state, and you have up and down spins at the ends, which is like the perfect swap operation. And this is the effective interaction that you get between the end qubits. So this I'm just showing you to show how complicated or simple this is. But the thing to remember is that what it does is that it just adds a phase. Like here, I have considered only the JXY and JYX components of the anisotropic exchange coupling, and this just adds to a phase, which can be shown by doing, say, 2-qubit calculation. And you will see that if you have the JXY and JYX components, then the state tends to oscillate between the up-down and the down-up states. So you remain in the same subspace. You have no change in magnetization. So this is effectively like the Heisenberg Hamiltonian, and where you have the same state transfer, but at a delayed time. So it kind of adds only a phase. So this looks like an ideal scenario where in the presence of the spin-orbit interaction and the DM term, you can actually get good state transfer. So how can we achieve this? This is what we tried to understand in our work, and it turns out that it is possible if we can orient the spin-orbit axis, which is this NSO, along the z direction, so that I have just the JXY and JYX components of the exchange coupling. And this NSO is related to the direction of the electric field, the externally applied electric field, which is very much controllable in an experiment. So suppose you have like quantum dots along the x-axis and the electric field is applied along the y direction, then you can end up with NSO along z. Now coming to some numerical results. So for the isotropic case, or for the electron hole spin qubits, when you have these diagonal couplings, you can see that you have perfect state transfer. But now, when you have the spin-orbit axis in any arbitrary direction, for example, in this case, or you have a random anisotropy, then you can see that the fidelity drops significantly, and which is below 0.6 and doesn't really make sense. But one can actually tune this spin-orbit axis along the z direction. Then you have an ideal kind of anisotropy, which again tends to give you perfect state transfer, which is same as the isotropic case. Here I have considered some small defect in aligning the electric field totally in the y-axis direction, so you have some x and y components, but as you can see, the results are very robust even to small changes in alignments. And the effective Hamiltonian that I found analytically, also the results from that also matches quite well with my numerical findings. So, and our findings actually hold quite well, even if we take a modular of the simple structure that I showed you, that when you have a tuned anisotropy, you have state transfer, which is same as that for the isotropic case. And this holds even when you increase the length of the quantum buzz. Also, we have checked that by adding small disorder, which is introduced in the form of small change in the exchange coupling, these results are quite robust. So now you can say that you have the best of both worlds. On one hand, since you are using whole spin qubits, you can have good qubit control and low hyperfine interaction with the nucleus, as well as good state transfer. So this brings me to the end of the first part of my talk. For the next part, I'm going to tell you about how temporal interference enables quantum state freezing in programmable atom arrays. So this was a work done. This is a work done in collaboration with Sugato and Rupayan and Ben, who is a PhD at UCL, and Bhaskar, who was also at UCL but recently moved back to India. So this was kind of more interesting to us because for most of us, this was the first time we were actually using a quantum simulator, and we were very happy that we could see our results in experiments. So in order to understand temporal interference, let's take a step back and go to Landau's inner transition, which I think most of you are familiar with. So what happens is that when you have a monotonic protocol, and you change the system parameters so that you move through a critical point, then the state transitions from a ground state to an excited state if you move fast. But now what we were doing is that we had a non-monotonic protocol, so we were going through the critical point twice. While passing through the critical point for the first time, some of the amplitudes undergo the transition where some of part of the state remains in its original state. And now before reaching the second critical point, both these states tends to evolve with different phases which interfere at this next critical point to give you the interference pattern, which is the Landau-Zinner-Stuckelberg interferometry. Here psi is basically the Stuckelberg angle, and sine square phi is what gives you the interference patterns, and depending on the phase that you gather, you will have either constructive or destructive interference. So this is what we looked at in our work, and we were trying to use this quantum interference to actually do dynamical quantum state freezing. This is something which has been shown for single qubits, for example, gallium arsenide charge qubits or Majorana qubits. But so we wanted to ask the question, can we see in Rydberg systems which display this many-body version of it? And this is something which is important because like interference and superposition forms the crux of quantum state preparation, and dynamical interference lies at the heart of Fluke engineering. So there have been like very recent work where they have done Fluke engineering in these Rydberg systems, but no one have really looked into the microscopics of it, and which is something we actually did in this work. So we have the standard Rydberg Hamiltonian, where delta is the detuning, and here omega is like the Rabi term, and you have the long-range interaction. So we start from the vacuum state, and in order to characterize how much excitation we generate as a result of this drive, we use the excitation density. So since we are periodically driving the system, one would expect to get a lot of Fluke heating, and which we show actually we don't at certain frequencies. So we have tried this for various geometries because this was done on QRS Aquila. And we have done for various geometries. So for few, the freezing was good. For others, it was not. But then you can tune the parameters to actually get good freezing in that case as well. I'm not going to discuss the details of it. So this is the result for the chain geometry. The green and the orange lines that you have here, or the yellow lines that you have here, are basically the results from the PXP model, this standard PXP model for a L equal to 14 chain, where you use the strict Rydberg blockade constraint. But now, when you consider the long-range interaction, and this red line here denotes the behavior of excitation density as a function of frequency for L equal to 14, and the blue is actually the results that we simulated on the quantum hardware. As you can see that they agree quite well, and as a function of frequency, at certain frequency, you have this dynamical freezing of these vacuum states. So we used two kinds of protocol. One was a single drive, where we drive only the detuning term, and also in the next one, we drove basically we have given a drive on the detuning as well as the Rabi term. So in doing so, what we see is that when you have a double frequency drive, then not only at the certain frequencies are the excitation suppressed, you have an overall suppression of the excitation density compared to when you have a single frequency drive. So these are the results for chain, and we also simulated the square geometry and also the hexagonal geometry. And as you can see for this cases as well, we have dynamical freezing at certain frequencies. So this brings me to the end of my talk. And to tell you about the importance of this work, what we checked is that the interference patterns are quite sensitive to change in the interatomic spacings, which actually shows that it has good application in precision sensing. And also to end this talk on the theme of this conference, which is quantum annealing, what we achieved in this work was temporal interference, which also governs non-adiabatic quantum annealing, where the system traverses avoided crossing at finite speed. So by engineering, when this dynamical phases accumulate versus cancel, one could accelerate quantum state preparation. So with that, I would like to thank you for your attention.
All right, thanks, Madhumita. Are there questions from the audience? Yes, one.
Thank you for the nice talk. So I was wondering, a couple of slides back, the frequencies where you observed this freeze-out, can you predict them somehow, or do you have like?
Yeah, we did an analytical calculation which kind of predicts the frequencies where we have the dynamical freezing.
Oh, thanks.
Any further questions from the audience? I see none, but I had one. In the experimental, or like in the simulations on the QuEra device, did you consider a noise model? So do you compare your theory like with noise to what you get from the device, or did you find that you don't need to consider errors in the device to get the agreement?
What is that error called? We considered spam error. We considered spam error, but the change was really small. So
okay.
There was no noise model.
No.
All right. So you cannot consider the atoms fixed. You don't need to care about thermal. Okay. That's pretty cool. Yeah. Thank you very much.
Thank you.
Okay. Then let's thank Madhumita once more.